Hello, everybody who's watching at home, and I need that squeaking to actually stop. Thank you very much. How are we all this morning, this evening, whenever it may be, wherever you may be? Probably this morning, if you've tuned into a HSC, well, this afternoon actually, if you've tuned into a HSC live stream. But you know, I'm not here to judge. I'm here to help with some maths. So we're already a couple of people watching, which is fantastic. So 2 days to go till the big one, to the big showdown, and then 4 more days until the what do you call it? The other exam, the Extension 1 exam. So I think it's time that we actually jump in and start doing some problems. What do you reckon? So I thought we might start us off with some integration this morning. Now I've gotten a new whiteboard because the Microsoft whiteboard just wasn't doing it for me the other day. So I've got a new whiteboard. And so whilst I learn how to do that, to use it, we will be good to go. So Defective Wisdom in the chat for the Twitch chat even. Do you want to send us through your financial maths questions? Because starting us off with some financial maths is definitely one way to really hinder my soul. But yeah, shoot them through and we'll have a look. We will have a look. I wish there was an easier way for me to get you guys to submit questions. Need to find a question sheet? No worries at all. While you do that, we might have a go at doing a integration question. There we go. I don't know how that looks for you guys. Oh, that's pretty nice. Yeah, I like that. It's good. Alright, we'll have a go at this first, and then Defective Wisdom is going to ask us a financial mathematics problem, which, we'll have a go at. I can't promise anything, but we'll have a go. And then HSC question 2015 question 14C. Cool. Alright, well, let's start off by looking at that, actually. That might be more fun than the integration problem. And then that way I've actually got something to go for. Question 9 and question 10. From which one, Detective? Alright, 14C. Oh, that's right, these are the old school ones. They've changed the new exam, so you've actually got a writing box underneath them. Can I access the link? No, I can't, sorry. Hang on, I can turn links on though. Give me 1 sec. Just have to bear with me for a moment. It's only following. Follows only, pop out. Deleted messages, chat parents. I'm sure there's a button that tells you that you can send a link. I'll tell you what, jump over to my YouTube channel, same name, and post it in there, and we should be able to find it. We should be able to send it across. In the meantime, we'll look for this question 14, part C. Ooh, some financial maths, some heavy duty financial maths. Okay, so I'm presuming this is it. So we have Sam, okay, and Sam borrows $100,000 to be repaid at a reducible interest rate of 0.6% per month. Let A(n) be the amount owing at the end of n months and M be the monthly repayment. Okay, cool. So, what we need to do is, just give me one sec. Okay, so show that A2 is equal to this very gross equation, which is not too bad. Okay, so pretty straightforward. I think. So the idea is that you're going to be making a recurrence relationship, right? So part I and part II are pretty straightforward because you're just creating the recurrence relationship. For part I, it's for it is for for 2 years or 2 months, sorry. And then AN for part 2 is just what it is after, whatever you want. So what we're going to do is we're going to create this recurrence relationship. And the way we're going to do it is we're going to start off by looking at, well, what A1 is. Because if we can work out what A1 is, we can work out what A2 is, just by using the amount. So, the amount owing, so if you think about it, if you start off with $100,000, okay, start with $100,000, and it's earning 0.6% per month, okay? So the 0.6%, you can write as 0.006, okay? It's the same in decimal form, okay? And the amount of money that's going to be in the account after 1 month, well, you just think about the compound interest formula, or just the interest formula, simple interest formula. I is equal to PRN, so the principal, 100,000, the rate, which is 0.006, and then the term, the period that this is going to go over. Now, for us in this particular case, it's just the 1 month, right? So this is the whole equation, right? Sorry, we want to compound, not just interest. 1 plus 0.006, okay? And our power of n is just 1, right? So it's our compound interest. So P, hang on, let me do it like this. Oh, this is going to be hard to get used to. So, compound interest formula, because I think it tells us it's compounding. Or in most cases it would. So compound interest formula. I'm not sure if this is on your formula sheet or not, but the amount is equal to P1 plus R to the power of n. Okay? And so we've got our 1,000 being our principal amount, our 0.006 being our rate, and then our n is 1 in this case. So our A1 is just equal to 1,000, and we're going to leave it like this, okay? Because we're going to be using this. We're going to be using this formula, well, this like notation later on. But the amount that you will have after a month in the account that you're borrowing from is less than the amount that you're going to be paying. So if you're repaying a specific amount after the interest has been calculated, you're going to be subtracting that away. Now, because we don't know what that amount is, we're just going to leave it as M. Now, for the second month, okay, we've got to take the amount that's in the first month, so our A1 value, whatever it is, okay, and again, we're going to multiply it by 1 plus r to the power of n, so 1.006 to the power of n, and then we're going to subtract our monthly payments again, right? Now, what we've got to do is substitute our A1 value in, because the idea is we're just using the compound interest twice. Okay, A2 is just using A1's amount, the amount that's left over. Okay, so A1 is 100,000, 1.006. Okay, so this here is A1, so this here is what A1 is equivalent to. And then we're going to be multiplying this number 1.006, okay, because it's the amount. So the A1 amount is the 1,000 times the 1.006. Oh, sorry, missed one bit. Minus that monthly payment. Oops. Minus the monthly payment from A1, okay, and then we're going to be timesing this by 1.006. Okay. And then whatever that is, we're going to subtract away from the month, okay? From the monthly payment as well. So from here, okay? From here, we're going to expand the brackets out, essentially. So what happens when we do that? Well, we get 100,000, sorry, times 1.006. And it's to the power of 2 because we're multiplying this guy here by everything on the inside, so by both the terms. So 100,000 times 1.006 times 1.006 is just the same as 100,000 times 1.006 squared minus 1.006 times m, and then minus the m that's on the end. Okay, and so rearranging this in a way so that we are factorizing the last bit, the m's, we get 100,000 times 1.006 squared, and the common factor is negative n, so bring the negative m out the front, and we've got 1.006 plus 1, or if you swap them around, you get 100,000 times 1.006 squared minus m lots of 1 plus 1.006, okay? And so that's part A. So what we've done here is we have we've shown what A2 is in general terms, okay? So M is our monthly payment. So whatever our monthly payment is, it's going to affect what all these values are, right? Okay. So that's part A. Any predictions for the major topics included in this exam? Not really, because because it's the second year of the new syllabus. There could be basically anything major in it. I'd be mainly focusing on your calculus, though. Your calculus is usually a big thing. That's always in the exams, because that's the thing that universities are most concerned about, is how well you can do your calculus, because a lot of your further mathematics and stuff rely on that heavily. Okay, part 2. Let's continue. We've got show that AN is equal to this guy up here. So what we want to do is show AN is equal to 100 grand times 1.006 to the power of n minus m lots of 1.006 to the power of n minus 1 over 0.006. Okay, so the way we're going to actually do this is we're going to do it by continuing the pattern from above. So next we're going to look at A3, right? So A3 is going to show us what this pattern's going to be, and this thing's going to turn out to be a recurrence relation. So as soon as you get problems like this, we're talking recurrence relationships, right? Because most financial mathematics problems are going to be turning into a number being taken away each time, okay? And so what we need to work out is, well, what's that number that's being taken away each time, and how can we turn it back into a recurrence relation problem that we know how to deal with? Okay, so let's try it for A3 and see what happens. So continuing this pattern, it's going to be the second month. So the third month relies what's on the account in the second month, times by 1.006, okay, minus m. So just like before. So whatever's in this the account after the second month, times it by the interest rate, because that's how much it's going to be gained, and then you're subtracting the amount, the monthly payment out at the end, okay? So substituting A2 in this from above, so that's this guy up here, we're going to get, and this is going to get nasty, 10,000 times 1.006 squared minus m, lots of 1 plus 1.006, okay? This is going to be times by 1.006, and then we're subtracting m from the above, okay? So it's the second amount, whatever the amount is after the second month, times 1.006, which is the amount of interest being earned, taken the month away, okay? And so this pattern's going to keep going, and this is going to go for 4, 5, and 6, but what we're going to do is we're going to simplify this particular one and see if we notice any sort of pattern, okay? So let's simplify this one, okay? I'm going to start off by multiplying the 1.006 by everything on the inside, okay? And we get 100,000 times 1.006 cubed, okay? Because the squared times the same value is going to give us the cubed. Minus, okay? Now, m plus 1.006 m, okay? And this is all being times by 1.006. I'm just going to rewrite it like this for now, okay? And then the minus the m on the end, okay? Now, simplifying that bracket that we just created, we're going to get 1.006m plus 1.006 squared m, okay? And then we're subtracting the m. And if you have a look, now we've got minus m lots of 1 plus 1.006 plus 1.006 squared, okay? And so you should notice in each jump, right, it's going up by a factor of 1.006 squared. And this pattern's going to keep going, and you can probably notice what this pattern's going to be. If I ask you what A4 is going to be, right, what A4 is going to be, so this is A3. A4, you could pretty much write it out just from the pattern, okay? It's going to be 100,000 times 1.006 to the power of 4 minus m, lots of 1, plus 1.006 plus 1.006 squared plus 1.006 cubed, right? And this pattern's going to go on forever and ever and ever. So we can generalize this now as an, and let's do an in a different color. We'll do it in a nice red, or whatever color this is, red, I think. So our an value now is going to be 1.006 to the power of n, so this number and this number are the same, and the highest number in this m part here is 1 less than the value it is. So it's going to be minus m, lots of 1, plus 1.006, plus 1.006 squared, all the way up to the nth minus 1 term. Now, how do we actually turn this thing here, this whole mess that we've got, into a formula? And that's exactly right. We're going to turn it into a geometric series because, well, not the whole thing, obviously, but we're going to turn part of it into a geometric series because we've got a geometric series at the back here. It's a series because it's going up by a specific number, and the number it's going up by in each jump is the same value, okay? We're multiplying by 1.006 between each jump. So yeah, this is just a geometric series. So now what you need to do is you need to get your geometric series formula out and put this part into it, okay? So the geometric series, okay, formula, I actually forget. I did this the other night and I got it wrong, so I'm going to look up the formula sheet because it is on your formula sheet, and I think there are two versions of it. I'm pretty sure. It's like I'm not going to say it because I'm going to get it wrong, and I don't want to get it wrong. This is also taking forever. I don't know why. There must be so many people looking at it. Okay, so the geometric formula is under series and sequences in series. Okay, and it's the one that looks like so there's the sum of the series, or the sum of the sequence, is equal to a lots of 1 minus r to the power of n over 1 minus r, okay? So this is the sum of a geometric series, the formula for a sum of a geometric series, okay? So what we need to do is we need to work out what our a value is, we need to work out what our r value is, and we need to work out what our n value is. Now our n value is just n because we're looking for a formula for the nth term, okay? Actually I'm going to keep doing it over here. So Sn is equal to, now our a value, okay, is the term that we start off with, which is the 1. The r value is the rate at which this thing is jumping up by, and it is jumping up by 1.006, okay? And so, remember our n value is just n because it's for a geometric series, or for a formula, sorry, that is being generalized for the nth term, okay? And then that number will just change depending on what we do in our formula. So substituting these values in, we get a, which is 1, lots of 1 minus 1.006. Now there is another formula on your formula sheet too, which has these in reverse. So like the Rn minus 1 and R minus 1. It doesn't matter which one you use, you'll get the same answer regardless. But just keep that in mind. Over 1 minus 1.006. Okay? So my bottom line is going to be negative, but my top line will be negative as well. And it won't actually matter which way it goes, as I said before, because both will work. Now, that means that we can now finish off our sequence from before, our formula from before. So an is going to be equal to, so what we're going to do is we're going to put that first bit in because that's just a value, and it's a finite value that we don't have to add up to infinity, or potentially, minus, and now we can replace this guy here, or more particularly this part in here, with the sum of our geometric series. So it's going to be minus m, whatever our monthly payments are. We don't know what those are yet. This is still in generalized form. But it's going to be m, lots of 1, well, we don't need that 1 minus 1.00, whoops. 006 to the power of n over 1 minus 1.006, okay? And so this is the formula now for our a-nth value, our a-nth term, okay? So our a-nth term is equal to this. Now, hopefully what that means is if we go back and have a look at the form that they want us to put it into, you can see that we've got exactly what we want. So we've got the 100,000 times 1.006 to the power of n, which is this first bit. Oops, this first bit down here, and then the minus, and then the sequence that we had. Now, I think they've got their sequence around the other way, which is fine. Okay, so what we need to do to amend that is just swap the values around. And you can do this. This is 100% okay, as long as you swap both the values around. Okay? Because they give you the exact same sequence. And both of these formulas are on your formula sheet. Okay? Like both forms. So 1.006 to the power of n minus 1 over 1.006 minus 1. Or I think it's 0.006. Well, I'll leave it like this, 0.006 minus 1, and then you can finish that last bit. Okay? And so this is the form, right? And you're allowed to do that. Both of those formulas, like both of these sum formulas, so this guy here and this guy here, these are both on your formula sheet, okay? So you don't have to use one or the other. For which one you should probably be using? You should probably be using the one which the number on the bottom gives you a whole number answer, okay? So one that gives you a whole number answer. Sorry, not a whole number, a positive answer, okay? Because we don't really want to deal with negatives when it comes to this. It doesn't matter, but better to stay safe. All right, let's have a look at part C. Part 3, I'm going to take a snippy of this and put it down here. So Sam makes monthly repayments of $780. So we've been told what the n value is now. Now, the cool thing about these particular questions, okay, if you don't know how to do part 1 or how to do part 2, okay, if you don't know how to do these, you can write them off. Does that mean that you stop there and you move on to the next question? 100% not, because question 3, like they've told you what the formula is that you need. Question 3 is a very, very easy question because you're just substituting these values straight into the formula they give you. And the reason they give you the formulas that you need to work towards is basically to say, hey, have a go at doing this and trying to come up with the formula yourself. But if you can't do that, that's okay. You've got this, this extra bit to have a go at. So, if we have a look at this part now, part 3, here's our formula from part 2. In part 3, we've been told some things about this guy's account, okay? We've been told he has monthly repayments, so that's our M. M equals 780, okay? Our N is 120 months, okay? So show that after making 120 monthly repayments, the amount owing is this to the nearest $100. So all we've got to do is just take these two numbers and substitute them into this formula. So the amount after 120 months is equal to 100k, 1.006 to the power of 120, minus the monthly repayments, which is 780, times 1.006 to the power of 120 minus 1 over 1.00, well, we can simplify that now, 0.006, okay? And so all you've got to do then is just work out what your answer is by putting it into your calculator. So get the trusty old Casio or Sharp out, whichever one you've got. So I've got my trusty calculator here. I'm going to throw this whole thing straight in. So 100k, 1.006 to the power of 120. Okay, minus 780, lots of, and this is going to get big. So 1.006, and we want that to the power of 120 as well. minus 1 over 0.006. Okay, so this gives us an answer of, damn it, $68,499 and 46 cents. Okay, which is equal to 6,800 to the nearest $100. Okay, so that's how we get the formula. Okay, so if you didn't know how to do part I and part double I, for part 3 or part triple I, you just have to substitute those values into the formula they give you. Okay, that's why they tell you what the formula is. Okay. Hey there, Sam. I hope you're enjoying your afternoon. Getting some math study done. We all love our math study, don't we? Alright, now the big three-parter. The big three-parter. Okay, we'll get rid of this calculator. We don't need it now. Or yet, anyway. Immediately after making the 120th payment, Sam makes a one-off payment, reducing the amount owing to $48,500. The interest rate and monthly repayments remain unchanged. After how many more months will the amount owing be completely removed? Removed? Repaid. That's probably more of a word that goes with it. Thank you for your efforts. Oh, it's okay. I'm just here to help. Just here to help. Alright. So I'll finish off this question, and then I'm going to have to dip for probably like 5 minutes to just do some work around the house, but then I'll be back. We're going to go till 2:30 this afternoon, so we will be here for a fair bit. Thank you for the tip, by the way, Unsure. That was really, really appreciated. I didn't hear that. But no, thank you. That's fantastic. Alright, immediately after making the 120th payment. So, what are we actually asking to happen? Like, what are we looking for to happen? Okay. Well, in this particular case, we're now looking not for a monthly value, because we are trying to find the monthly value, but the formula, or the form that we're looking for this thing, is we're looking for when this formula, this sequence, this disgusting big thing, when this guy is equal to 0, okay? Now, the amount that he has owing after the specific amount, because we're essentially asking how long does it take after he gets to a specific value. So our new AN is equal to 0, or our new AN formula, okay? The principal amount, the amount he's starting off with, it's not the 100,000 that he's starting off with this time. He's starting off with only, well, I say only, it's still a lot of money, but 48,500, okay? Now, our N value is still unknown, we don't know what that is, and the other things stay the same. So our rate is still 0.006, and so like those values, so the R value is still the same, the N value, we don't know, but the principal value is the amount that changed. So our new formula, so our new AN formula, is going to look like this. It's going to look like 48,500. So instead of the 100,000 that we had before, it's the exact same thing, but with... Oh, and the monthly payments is still 780, is the other thing. You know something else, I just couldn't quite remember. Now, what's going to happen is we're going to have to solve a very, very, very big, disgusting formula, okay? Very, very big and very, very disgusting formula, okay? So we're looking for when AN is equal to 0, and this is what AN is equal to. So essentially what we've got is we've got this being equal to 1.006 minus 780 over 0.06, okay? And from here, where's my mouse? From here, what we can do is we can rearrange it a little bit so that we can move the whole lot of this fraction, okay, 1.006 power of n minus 1 over 0.006 being equal to 48500. And I can do this because I'm just adding to both sides, right? Like I'm just adding 780, like it's negative 780, all that stuff, and I'm just adding that whole thing to both sides. Cancels out on that side and becomes positive on the right-hand side. Now the issue is that we're trying to solve this thing for n, okay? And we've got two n's. If you have noticed, we've got an n up here and an n up here. And so what we're trying to do is we're trying to work out, well, what is this n value equal to? So what we're going to have to do is we're going to have to do some expanding and some simplification to get what this n value is, okay? So the right-hand side, left-hand side, we'll start with first, because it's very big and gross. Okay. Now, what's the best way to do this, actually? What's the best way to tackle this? Let's expand the top. So we get 7. We're going to get 780 times 1.006 to the power of n minus 780, okay, because it's 1 times that, and this is going to be all over 0.006, okay? So if you're not sure how to do that, when you're multiplying something on the outside of a fraction, just times this guy by the thing on the top, okay? That's all you've got to do. Now on the right-hand side, 48,500 times 1.006, okay, so that remains unchanged. Now what we're going to do is we're going to move the 0.006 on the bottom of the left-hand side to the right-hand side because we don't like dealing with these fractions, yeah? So, get the old trusty Casio out. We love the Casio. He's our favourite. So we're going to get the trusty Casio out and we're going to do the next bit. So we're going to multiply both sides by 0.006, eliminating it from this side, but then changing the right-hand side to something not as nice. Okay, so we get 48500 divided by times by 0.06, otherwise it get very, very big. Okay, and that gives us 291. So this right-hand side becomes 291. Lots of this, okay? So I've just multiplied both sides by 0.006. 0.006. Now, if you were to accidentally divide it by that, think about the number that you're going to get in return, okay? So this is just like my little teaching moment. Like, if you end up with this, remember we're trying to work out when this thing is getting to 0. And if you end up with a number of 291, that sounds pretty reasonable. Our number's getting smaller and smaller and smaller. If you end up with an answer with 8,083,333, you could probably assume that something has gone wrong because that's a really, really big number. Okay? And it's outside the scope of what they've borrowed. Like, he's only borrowed 100 grand. $8 million popping up somewhere in our formula probably means that something has gone wrong. So 291, we're pretty happy with that. Okay, now solving just a simple equation. You guys should know how to do this. We're going to add 780 to both sides, right? So add 780 to both sides, we end up with 1.006 plus 780, okay? So just solve the rest of this like a simple equation, yeah? Now, what I'm going to do now is I'm going to move this guy here to the left-hand side, okay? Now, as it stands, this is just a number, okay? If I gave you the problem, I've got 15 is equal to x plus 3. How do you solve this, right? Okay. Well, you'd move, you'd subtract the, oh, this is probably not a good example because I don't want to move the thing, I'm trying to move the thing across. Let's say you had it like this, plus y, okay? 15 is equal to x plus y, and I want to make y the subject. What do? You subtract x from both sides, right? Remember, this guy here is just a number, okay? So what I want to do is I want to move that guy to the left-hand side. And the way I'm going to do that is I'm just going to subtract it from both sides. That's all I'm going to do. Okay, so let's do that. 7. I'm going to need some more space. So this is 780, lots of 1.006 to the power of n, minus 291, 1.006 to the power of n is equal to, well, 780, that's still there. Okay. Now, this problem is very simple. We've got n's in both the spots, and we want to condense it so we've only got one right. So we've got an n on this in this part and an n in this part. But this is just saying I've got 780 lots of 1.006 to the power of n's, and I'm trying to take away 291 lots of 1.006 to the power of n's. These two things are exactly the same, yeah? So, to simplify this, all I need to do is just subtract. That's all I've got to do. 780 take away 291. Okay, and because my brain's not working to its full potential, we get 489. So this just becomes 489 lots of 1.006 to the power n, which is equal to 780. Okay, next step, we're going to divide both sides by 489. And I'm just going to leave it like this for now. I'm not going to simplify it just yet. I'm going to leave it like it is. Am I? Yeah, let's leave it as it is. I like dealing in absolutes. I'm like a Sith. Deal in absolutes. Okay. So then finally, what we're going to do now is we need to get the n down from the top. Okay. So little bit of a trick to this. Okay. What we do to do this bit is we're going to take some logarithms. Okay. So this is probably the tricky, well, probably not the trickiest part. This is quite a tricky ending to this long solution. What we need to do to pull the n down is we're going to apply a logarithm of both sides. Now, it actually doesn't matter which logarithm you use, if it's a base 10, a base e, a base 2, like it's up to you completely. But the way we're going to do is we're going to just apply a log of base 10 because that's what's on the calculator. Okay, so apply, whoops. So apply a log base 10 to this. Oh, and to both sides, of course. You can't just do it to one side, you got to do it to both sides. .006. Nope, doing the wrong thing. 780 on 489. Okay, and I should actually rewrite this one so that the n is on the inside, because we want the n to be on the inside. Because we're taking the logarithm of this whole thing, right? Now, using our log laws, when we have a power in our log, how do we get that out? Well, comes down the front, right? So n log base 10 of 1.006, okay, is equal to this side here. And then finally, to get the n by itself, we my pen's really being really weird. So to get the n by itself, what we do is we are going to divide both sides by log of 1.006, okay? So, hopefully now, what that means is, if we put this into our calculator, so log base 10 is just the log button on your calculator. You can't see this. Turn it on. So the log base 10 on our calculator is this guy here. Okay, this is log base E, this is log base 10. We're going to put this whole thing in, 780 over 489. Thought I deleted it all for a second, I was going to be sad. Over log of 0.1.006. For 0, we can get an answer. And when we press equals, we should get a number. Don't actually draw a smiley face that you guys didn't see me draw. But 79 months to fully pay it off. Okay? So that was a very, very, very long-winded problem. Okay, so HSC 2020, all of question 29, please. Yep, no worries, we can have a look at that one. And advice on rounding when they don't tell you what you should do. Everyone does it differently. If you are rounding... Okay, so there's a few different situations for rounding. I think, anyway. And this is just my personal judgment. Most of your... Thanks for your help, no worries. More than happy to help, that's why I'm here. Most of your rounding, what happens is... you have different situations where different rounding techniques may be useful. Now, in most cases, the rounding's not going to matter too much because the markers, the HSC markers, and I know a HSC marker, by the way, too, so I'm not completely bullshitting, but I do know a HSC marker who has said that, you know, they get a sort of like a boundary that they mark around. Like, it's not just a, you're marking... You know, it has to be this exact answer, and if you get 0.1 either way, you get it wrong. Like, it's 100% not like that. If at the end of an answer, you round it to, say, 2 decimal places, and they don't tell you to, that is 100% fine. You will still get the full marks. You don't have to write out the whole calculator input, okay? So, for example, I wouldn't have to write out this whole thing, and in this particular case, my 79 weeks would be more than enough. I was 055, but anyway. So, that's the first situation. The second situation is when you round in your answer. Now, what you will notice is when I did this fraction here, I left it as a fraction because if I was to change this to, say, something that was rounded to 2 decimal places, like, I don't know, it's close to 1.52, let's say. It's actually going to change the answer I get down here, okay? Not so much so that it's going to affect the final answer too much. And again, they will take that into consideration, and if they see all the steps and see the answer you got, they will give it to you, like 100% they'll give it to you, okay? So, for me, what I like to do, if this number on the inside of your calculation is not too gross, I leave it in its inexact form and then don't round until the end. That will give you the most exact answer, okay? If this is something gross on the inside though and you don't want to write it 100 times, there's 2 things you could do. One, you could round it and that would be totally legitimate, you're allowed to do that. Or you could say, let 789 on 489 be equal to t or something. And then just use t until you get to your final answer. And then do it like that. And that's just a shorthand way. Instead of having to write 789 over 489 each time, you could just go, okay, well, this is log 10 of t. And then this down here is log 10 of t over log 10 of 1.006, okay? And so it takes out a little bit of the work. And if it's something really big, long, and disgusting, then it's, you know, like it makes that shorthand a little easier. And then you put the full thing in when you do your calculation in the answer, okay? Anyway, hopefully that has helped. At the end of the day, the rounding's not going to matter too much. 2 decimal places, don't round to 1 unless it says otherwise. 2 is probably your minimum overall though. Unless the answer, like for the question we just did, how many months does it take? Like, you're not going to say 78.005 months because, well, you don't pay things off in 0.005 months, right? So what you would do in this case is you would say, okay, well, he still has a bit owing left, and he's not going to make his last payment till the month after, so it's 79 months, and that makes sense. So 1, think of the situation. 2, round to 2 decimal places. Well, try not to round throughout your answer, and then 3, round to 2 decimal places if it's going to be too hard. Okay, so what's going to happen now is, are you able to go through the Abbott Slay 2021 paper if you have time? I'm not going to have not time today, but I'll be around tomorrow. Tomorrow I'll be on pretty much all day, so I'm going to spend the whole day just chilling, waiting for you guys to throw messages, questions out. So, what we'll do is, we can have a look through that tomorrow, the Abbott Slay 2021 paper, if I've got time. The only issue is I'll have to find a copy of it. I can't just magically make one appear. I'd have to find a copy of it. I've got a website where I can look, but I'm not 100% sure I would be able to find it. So, what we're going to do is we're going to have a bit of a break for a few minutes. And you can send me a link. Okay, that's fantastic. Can you send it through the chat? I'm curious. So try sending it through the chat. Anyway, I'm going to have a break for probably 3, 4, 5 minutes. And I'll be back and we'll go through some more until about 2:30. So give me a little bit of a break and then we'll be back to keep going. Okay, I am back, which means it's time for maths. Headphones. Alrighty. So what I thought we might do is we might have a look at question 29 from last year's HSC. If you do want to watch last year's HSC though, I did already do a video on it, but we can go over it again. Yeah, why is my music also stopped? Oh, there it goes. Ask and you shall receive. Ask and you shall receive. Maths Advanced. That's HSC exam paper 2020. Question 29. Probably be halfway down the page, wouldn't it? That's right. I remember this guy. This is a toughie. Oh, we'll have a crack at it. Be good fun. Have a crack. Have a crack. Have a crack. Okay. Alright, so we've got the diagram shows the graph of y is equal to c times log of x, where c is greater than 0, and show that the equation of the tangent at c is equal to that when x is equal to p and p is greater than 0. Okay, so immediately we see the word tangent, we see the word tangent, we think of the word calculus, or differentiation in fact. So, I'm going to be doing some differentiation, and we've been given a point, okay, the point being 1, 0. Very, very important. By the way, too, little hint, HSC hint, when you are sketching graphs, please make sure that you plotting all important points. Okay, so plot all your important points. Could you do this after? Please prove that cos x plus cos 3x plus cos 5x plus up to cos 2 is equal to sine 2 of n of x over sine 2 sine of x. I could give it a go. Is that extension 2 stuff? Induction. Okay, it is induction? Yeah, cool. Oh, well, that makes life easier. That's for sure. Cos x plus cos 3x plus cos 5x. That's extension 1, yeah. So I am doing extension 1 streams next week as well, by the way. So if you want to tune into those, won't be as big as like tomorrow's one, but yeah, tune into those as well. But I'll do that. I can do that next. That's not an issue. But first, let's do this one, and then we'll have a look. Okay. So the diagram shows the graph of this, show that the line of the tangent is this, where x is equal to p and p is greater than 0, and they tell you what it is, which is nice and convenient for us. So let's have a go. Now, so we're going to be looking at some calculus, as I was saying before. So because it's a tangent, okay, and we're looking at the point, and we've been given a point, so some random point. So essentially we're generalizing this tangent, right? So some random point P. So show the equation of the tangent at C. Okay, so for the tangent, okay, we need two things. Okay, we need a gradient and we need a point, okay? We'll add a particular point. So let's start off with the gradient, I think. So the gradient is just equal to dy dx at x is equal to p. Okay. So if y is equal to c log of x, then dy dx is equal to, so this is just c times log of x, or natural log of x. And this is something that you guys need to remember, but I believe it is on your formula sheet too. The integral of the natural logarithm, okay, just 1 over x. Sorry, the derivative of that, not the integral. Okay, so if it's just c times that, where c is a constant, then this is just c times the derivative, so which is just equal to c on x, like that, okay? So c on x, pretty cool. So that's our gradient. Now, sorry, that is our gradient formula. So now for our gradient, our m value, we're going to substitute p into this guy here. So our gradient is just equal to c over p, like. Nice and simple, okay? Now, once we've got that, we need a point. Okay, so let's find our point. So our point is xp, okay, and with our gradient m being c over p, we can now substitute this into the point gradient formula. Okay, so basically this is just another version of the gradient formula. And what it does is actually allows us to find a line where y and x are just our y and x values of the function. Okay, substitute these points in, so if we call this x1, we call this y1, and our m, we get y minus p is equal to c over p, lots of x minus x. No, it can't be right. X minus p, sorry. Wait, hang on. Oh, wait. Big off. So the point on the gradient formula. I always get this wrong for some reason. So we don't want this point here. What we want is... So our m value of our gradient is c over p, and our point at x is equal to p is, so we're substituting this guy into the original equation, okay? And our original equation is up here. So this guy is going into this. Y is equal to c log of x, okay? So we're going to substitute that into y is equal to c log of x, and therefore we get y is equal to c log of p at x is equal to p. There we go, so that's our point. So we've got our x value, which is p, we've got our y value, which is c log of p, and we've got our m value, which is c on p. So now we can substitute this into our value. So this is y1, this is our x1, and our m, so c log of p is equal to c on p x minus, and our x1 value is p. Okay. So from here, all we need to do is just rearrange it for y. Okay, so let's expand the right hand side, and we get cx on p minus, well, p is 1. Okay. Sorry, c. Because we're timesing it by c on p. Okay. And then from here, we get, so we add c log p to the right hand side, cx on p minus c log of p like this. Plus, sorry, because we're adding it to both sides, and that's it. Yeah. Okay, so that's part A done, which was showing that was equal to this. So yeah, once you substitute those three things in, so you're looking for your m value gradient by substituting x into the derivative. Your x value and your y value is just substituting your x value into the original equation. Okay. All right, let's pull up question number B. Question number B. Okay, so we'll paste this in. We'll do it properly. Okay. So find a value of c such that the tangent from part A has a gradient of 1 and passes through the origin. Okay. So we're looking for when the gradient is equal to 1 and it passes through the origin. So the origin, is our point 0, 0. Okay, if we actually have a look at the graph as well. Okay. Passes through the origin. Ooh. Oh, sorry, the the tangent, isn't it? Yes, the tangent. So we're looking for when the tangent, so when we draw a line, passes through this guy here, right? So if I was to draw a tangent, it's going to pass through that. So we're looking for the gradient at which that happens. Oh, sorry, when the gradient is 1. So we know from before that the line, the tangent, so the general form of the tangent, so when it's equal to 1, but m is also equal to c on p, right? So this means that we're looking for when c on p is equal to 1, okay? And this only happens, of course, when c must be equal to p, okay, by just multiplying both sides by p. So the tangent and the gradient is equal to 1 when c is equal to p, okay? And so to find when the tangent passes through the origin, we're going to substitute 0, 0 into the original equation, right? So, well, into our tangent equation, I should say, not the original equation. So minus c plus c ln of p, okay? So, since it passes through the origin, we know that's going to be 0, 0, and this is going to give us a value, hopefully, for p that we can work with. Okay, so this is going to give us 0 is equal to 0 minus c plus c log of p, okay? Now let's rearrange this, okay, a little bit. Do we need to rearrange it? No, let's leave it as it is, okay? Because what we're going to do is we're actually going to be trying to find our value for c, right? So minus c plus c log of p, okay? So to find our values for c, all we need to do is factorize this now. Okay. So to factorize this, take the common factor of c out. So it's going to be c, negative 1. Do we going to take the negative out as well? No, we're going to leave the negative in there. Okay. And so we get to two equations now. So c, so when is this thing equal to 0? Sorry, log of c. Log of c? Yes, right, of course. So, because we also know that, because we're trying to find values of c, right, and we also know that p is equal to c from up here, yeah? What we can do is we can substitute that guy down into this bit here, which is what we want to do, okay? And this is going to change our equation so that we don't have c's and p's. It's going to change it so that it's all in terms of one value, okay? So we're going to rewrite that as log of c, okay? I knew there was a reason why we needed to change it to a c, and that's why we did the bit at the top. So to remove the p values, we can change into c's, and now we can find the value of c for which this works. So our c values now, okay, well, when are they equal to 0? Well, this is only equal to 0 when either this part's equal to 0 or when this part's equal to 0. Okay, so either this or this. Okay, so this one, we know that c needs to be greater than 0 from the original question. So if I go back up and show you this bit, so p needs to be greater than 0. So remember, because p is equal to c, so if c is equal to 0, then p is also equal to 0, which means that does not satisfy this part of the equation. So we can essentially just ignore this part here, right? And we can focus. So we can focus on this guy. Okay, I'm going to focus on this guy. So this is equal to 0. So we just got to solve this equation like a literal equation. So log c is equal to positive 1. So when is log c equal to 1? Or when is log c, well, when is log of anything equal to 1? Natural log of anything is equal to 1. Well, when c is equal to, so, you know, e to the power of what is equal to 1? Well, e to the power of, sorry, what to the power of, I always forget this, so it's base, e to the power of what is equal to 1. Should be 0. We've got that already though. E to the power of 1 is equal to e, that's right. I've got to just quickly remember it. So we can rewrite this as, so remember, log ln is the same as log e of c is equal to 1. So in other words, e to the power of 1 is equal to e. Just trying to remember how the to change logs back into exponents. So yeah, so c is equal to 1, and so that's the value for which this guy is, the value for c which is going through the equation. So if you substitute it back into the original, that would actually produce the equation that you need. But you don't have to do that though. Okay, so you only have to show what value of c makes it so that the tangent has a gradient of 1 and that it goes through the origin. Okay, happy days. So could you please prove that cos x plus cos 3x plus cos 5x plus up to cos 2n minus 1 of x is equal to sine 2n of x over 2 sine of x. Oh god, I've got to remember how to do induction. Alright, so I'm going to have a quick go at an extension problem for those of you who are here for the advanced stuff. Going to have a quick go at it, see if I can do it. If not, don't stress. We'll quickly move on to something else. I'll just keep in mind though that if you are looking for some extension content, come by next week. So Tuesday, Wednesday, Thursday, I'm going to be doing some streams on those nights as well. So you can come and watch on those nights. Okay. So the question is, prove that cos x plus cos 3x plus cos 5x up to cos 2n minus 1 x is equal to sine of 2nx over problem. Well, I mean, extension 1 says prove, it's going to be induction. So, step 1, prove for n is equal to 1. So cos of x is equal to sine of 2x over 2 sine of x. I'm going to have to remember my laws, aren't I? Thankfully I have my thingo up, my trigonometric identities, because that looks like a good old 00 formula to me. Sine of 2x. Do I want? I want it to be equal to sine x, cos x even. Sine of 2x is the same as sine of x plus x. Sine of 2x is equal to 2 times cos x sine x. Yeah, of course. So, cos of x being equal to, so sine of 2x is the same as 2 sine x cos x over 2 sine x, and then thankfully that's very, very convenient for us to cancel some stuff. Bang, bang, and we get cos x is equal to cos x. Yeah, cool. So we're happy with that. Okay, now for the inductive step, the fun bit, the very fun bit. 2. So for the PDF question, could you go through question 26 of PEM paper? Yeah, that's no worries. What's a PEM paper though? It's the only thing I'm not 100% sure of. 2020 of PEM paper. Yeah, no, it's not a worry. We can do that. Assume that. If I remember how to do this. Assume that true for n is equal to k. So that is. It's a trial one. Okay, I'll have a look and see if I can find it. Cos x plus cos 3x plus cos 5x plus up to cos of let me just get this thing up. 2k minus 1 is equal to sine of 2kx over 2 sine x. Okay, so that's our assumption that we do, and so we need to then prove I'm going to prove that true for n is equal to k plus 1, so that is, and I'm going to rewrite it, cos x plus sine x. Why did I do plus sine x? I just, wow, that was weird. Plus cos 5x plus up to cos of 2k minus 1 plus, and then the pattern's going to continue as 2k plus 1 because it's adding 2 to the inside each time as it goes. Yeah, so if we substitute k plus 1 into that, we should get that is equal to sine of 2k plus 1 x over 2 sine of x. Okay. Now the cool thing about induction is that we can assume, because we've assumed part of this is true, we can take all of this guy in this part and we can replace it with this guy. So we can rewrite this line here as sine of 2kx over 2 sine of x plus cos of 2k plus 1 is equal to sine 2. I'm going to expand this out. So 2kx plus 2x over 2 sine of x, okay? So we all happy with that step so far? So basically all I've done is I've done the induction step, I've assumed that it works for n is equal to k, and so that means I'm saying that this thing is true. So wherever I see this guy here in sequential steps, I can replace it with this thing here, which is what I've done down here, which I'll highlight. So that's this guy here, okay? Now, I need to remember how to do the rest of this, because it's going to be painful. I can assure you right now. So we want the left-hand side to show that it is the right-hand side, or show that the right-hand side is equal to the left-hand side. I don't know what the best way of going about this would be. I mean, the right-hand side, you've got the double formula up the top, which we could probably expand out, so let's try that. So right-hand side. The old extension problems make me think a bit more. You get more time in your HSC per question for the extension questions, by the way, too. So keep that in mind. So we've got our compound angle. So sine 2kx plus 2x and 2 sine of x is equal to, so this would be the same as sine of 2kx cos of 2x plus cos of a, which is 2kx plus times sine of 2k plus 1x, right, of course. Yeah. That's because I can guarantee right now I would be looking for that, and I'd be very, very cranky if I didn't find it. Thank you for reminding me. Sine of, what did I say, 2kx? No, 2x. Sine a cos b plus cos a sine b. And it's going to be over 2 sine of x, okay? Okay. And remember, so this guy here is our goal. So we want some fraction plus cos 2kx, which I think is going to work out pretty nice, actually. So, let's break this up into two fractions. Sine x plus okay. Now from before we had that sine 2x is equal to 2 sine x. I'm going to try something, but I'm not sure if it's the right approach. So, for the right hand side, you guys might have to help me with the cosine one. Because 2kx times 2 sine x cos x over 2 sine x, right? And so that cancels out with that, yeah? So what's the left hand side? What's the cos of 2x on the left hand side? What's the double angle formula for roots? Because on my right hand side, if I continue that line of thought, you're going to get 2kx cos of x, right? So you've got the multiplicative of that. And when you've got the multiplicative of two cosines, you can rewrite this as a half cos 2kx minus x plus... What software is this? It's called Miro. I just found it online randomly. Can I spell it? M-I-R-O. It's gonna be something plus that, right? No worries. Could you use compound angles? Yes, you could, 100%. So I think when we use the compound angles on this point, it's going to break it up into something really disgusting, and then we'll be able to simplify that. It's just the right-hand side I'm not 100% sure. The left-hand, like the left-hand part of this, I'm not purely 100% sure on how to simplify just yet, but we'll get back to that in a sec. So this right-hand side, so this first bit here, use a different color, we'll use a green for it. So this guy, that's not a good green. It's going to be cos, so a plus b is going to be cos a, so cos 2kx. I feel like we're just going to go back in a circle though, but we'll have a look. Cos 2kx, cos 2x minus sine 2kx sine x. So that's this guy here, right? Now, let's do the other bit. Well, have I got that right around? I've done plus instead of minus, haven't I? So that's the purple bit, actually. That's what the purple bit looks like. If it's a minus, that's just going to... What does the minus do? Changes the angle. So it's going to be... negative 2 cos x? Cos negative 2x? Why have I put cos of 2x there, actually? That's another question as well. I think I made a little error there. I think it's just meant to be cos of x. And I think it's meant to be cos of negative x as well, because... because there's a negative in between them. So it's 2kx plus negative x. Okay, there we go, cos of... And then this one's going to be the proper one. 2kx cos of x. Minus sine 2k of x sine cos of x. This time. So the issue is we've got these negatives and positives, right? Oh, you'd be using your symmetry of functions, wouldn't you? So cosine, is that an even function? Cosine is an even function. So what that means is cos of negative x is going to be the same value as cos of positive x, right? Okay. So because cosine's an even function, cos of x is the same. It's equal to cos of negative x, right? So we can change those intermediately. So what we end up with is cos 2k of x, cos plus x, because it's the same as cos of minus x. Okay, does that make sense? So it doesn't matter which value I pick, if it's positive or negative, it's gonna produce the same value whatever the x is. Now for the sine part, now I believe sine is an odd function. So that means that this guy here is the same as plus the positive, okay? So just a reminder, even function. No, other way. And then the odd function. So you can change these intermediately. Okay? So these two things are equivalent. Now, because cosine is even, we can swap it like that, and because the other thing is odd. So that means we'll go back to my red. So this is going to cancel out with this, and it's going to leave us with the cos of 2kx, or two lots of the 2 cos 2kx cos x, and so that's just going to give us that, okay? Yeah. And what did we want? 2k plus 1. So now that we have this part, we just need to combine the two. So we've got the product of two cosines. Am I just going in a circle if I do the compound angle again? Cos A, take away that, plus cos of that, plus that. No, we're not. Okay, so now this simplifies to cos of I gotta get this right. So cos A cos B, it's gonna be half again. Factorize cos x. What do you mean by factorize cos x? Because... Oh, because it's cyclic on 2. On 2k, isn't it? No.
I'm wide awake at night without you by my side. I wish it was a lie. Did I waste your time? I know you won't be mine. How do I apologize? And it's been a while since I've seen you smile.
I don't think you can just factorize from that point.
I need
Oh, let's get the front.
behind, but you stay on my mind.
I mean, it looks very obvious you want it, like you can factorize that, but the issue is that it's 2kx on the inside, not just x. So you can't take a factor of cos x out. So I'm just trying to work out what the connection is between that and what we want.
Did you stop on me then? After all I've done for you.
Yeah, so it says here it's not always true when I put it in the Wolfram, so... there must be a connection between the two. I'm just not seeing. I want to go through all that again. Must be something I'm missing.
My world turns to gray.
So if I do another compound angle again, so the cos A, cos B one, what we end up with from here is half cos 2kx minus x, which we can then factorize, if that makes sense. Plus x. And then I think this is going to work here. So cos, so if we take a factor of then how do I get those two together? Because once we got those two together, we pretty much get what we got to answer by picking on the left-hand side rather than the right-hand side when n is equal to k plus 1. Okay. Let's have a we'll have a crack at that then, and we can see the left-hand side from the right-hand side instead. So working on this to get to this. I just like the look of this better because it was much easier to work with part 1. But well, for the first step. But obviously, as you can see, it's getting quite messy. It's just Alright, let's have a look at the left-hand side. Hopefully I can finish this soon, because I've got to actually get off soon, which is a shame, but, so 2kx. Okay, so let's have a look at the left-hand side. Let's see this again. Let's scroll it up. Left-hand side is equal to... cos 2k1x. I feel like I was getting really close, which is what really annoys me. This is how I feel about all extension work. You always get so close, and then... So we're clicking on this side. See, the only issue with this is I'm not 100% sure what to do with the top. I'm just not 100% sure what to do with this. But I'm presuming it's going to be something similar to what we had in the previous bit. Step 1. Well, okay, that makes sense. So you'd go... this would be 2 sine of kx, cos of kx. Is this true? Is this something you can do? Yep, so it's not 100% something you can do. Cool. Cool. And put all over one fraction. Would you... 2 sine x cos 2k plus 1x. Would you expand out the right-hand side using a double angle though? Before you put them all on one fraction. Is that what you did? Or you just put them straight over one? So in other words, did you like break this up? Did you break this guy up to be whatever it is? A half cos. Nope. Not that one. It'd be like cos 2k plus 1. Sorry, cos 2k. Cos of 1. Ugh. Maybe not. Alright, so what? Maybe to make it easier. Alright, I'll do that. I'll have a go and see what we come up with. So we've got cos of... So this will become cos of 2k. Cos of 1. Plus minus sine of 2k sine of 1. Okay, we'll just leave it like that for now because one of these terms is gonna disappear. It's cos of 1, sine of 1. Sine of 1 is 0. So it's this bit that disappears, yeah? Is it? Yeah, cool. Okay. So then we will put these over the same thing. Cos of 1 is equal to 1. Yeah, cool. So that disappears. Yep. And then so we're going to get 2 sine x cos of 2k over 2 sine x. Like that. And then you can tell it's been a long time since I've done trig like properly. Okay, so from here, we could probably combine these, because if we have a look at our formula sheet, one of the formulas that we've got is this guy. Which one do I want? I want sine cos. Sine cos, sine cos. They're not the same angle though, which doesn't work. Left hand side has the same angle, so sine A, cos A. So sine A, cos A. So what I'm going to do is I'm going to use this guy here. So this formula, which I'll just pop up next to it. So I'm going to use this guy here for that part, right? So the 2 is going to make that disappear. So it's going to become sine of A plus B. Now they're the same angle. So sine of A plus B, which is 2kx, plus sine of A minus B, well that's just going to disappear. So we get that first bit there, which is just sine of 2kx. Okay. So 2 lots of that cancels this out. Because if 1 is half, then 2 is just 1. Okay, now for the right hand side. The right hand side I think I could have left. No, it goes up there with it. Sine of 2k plus 1. No worries, Sam. Enjoy the rest of your afternoon. Sine A, sine B. And then I'm going to be using the same formula for the next one too. So I'm going to use this one. I'm going to use this for this one as well, but in green. So I'm going to use this for that as well. But obviously this one's going to give us something a bit higher. So it's going to be sine A plus B. So sine of 2k plus x, and then plus sine of A minus B. Actually, and then this is all going to be over 2 sine x. And now we can use some double angle formulas. Oh, looks like I've come to the end of this line. That's alright, we can just go over here. So the sine of 2kx we're just going to leave. And then some double angle formulas, so x plus 2k. It's going to give us... Do I want to do that? Or is that just going to turn it back into... No, it should be fine. Sine of a plus b. So sine a cos b. So it's going to be sine x cos 2k plus cos x sine 2k. I don't think this is going to help. I'm really lost, to be honest. I'm not going to lie. I'm just going to I'll keep trucking though. Side now. So sine of x minus 2k. Oh, and this will end up with our... Okay, so this, I think this will actually work. So sine of... 2kx. What are we doing? Sine of x. Cos of... negative 2k, which would be the same as negative 2 cos of a. Sorry, negative cos 2k. Plus, it's going to be cos of x. Sorry, no, it's going to be... Never mind. But I've got it. Sine of negative 2k. Okay, and this is all over. Two sines. Okay, so from here, so this guy here is the same as, so it's an even function, so this is the same cos of 2k, and this is an odd function, so this is the same as negative, so this will be negative cos x sine 2k, which is what I want. Now we're going to cancel some stuff out. Okay, this is looking good. So the minus cos x sine 2k is the same as cos x sine 2k, so those two guys will cancel out, so this term and this term disappear. Okay, the sine x cos 2k plus the sine x cos 2k, so this guy and this guy are going to combine to become 2 sine x cos 2k. Just tell me if I'm wrong, but I feel like that's what we started off with. No, I don't think so. Okay. And this is going to be equal to, so over 2 sine x, okay, which means we get, and I think this is actually the point where we get our fraction that we want. Sine 2kx over 2 sine x, and then that cancels with that on this side, so we're left with cos of 2k. Which is all, no, I don't think we wanted that. We wanted, wait, what did we want? We started with the left hand side this side. Where are we? Over here. No, that's not what we wanted at all. We wanted sine of 2kx plus 2x. Ah, dear. Dear, oh dear, oh dear. Actually, you could probably combine these guys. This was a very cruel question. It's a tough one, but I mean, at the end of the day, it's something you could be asked. It is something you could be asked, and you need to know it. So, what I'm thinking at the moment is who I feel bad for is the advanced people who tuned in and seeing all this and going, oh god, I hope I don't need to know this. No, if you're in advanced, you don't need to know how to do this. Just someone got a bit eager for their extension work. I don't want the plus to know. I wanted... So 2 sine x cos 2x, let's put it back into another formula. Sine cos, which is going to be half sine x cos, sorry, sine x plus 2k plus sine x minus 2k, which is, I feel like we had this just before, didn't we? Hang on, let me just make sure I got this right. Sine cos, sine of x plus 2k, sine of x minus 2k. So 2... Alright, I think I'm going to throw the towel in there. I just can't seem to get this to work, and I'm racking my brain trying to work it out. Plus, it's getting to the point where I need to actually get off as well. So, the last thing I just want to mention to you guys is that we've got one more day tomorrow where we'll be going through advanced stuff, and I'm going to hold myself and just do advanced stuff. I might have another look at this later on, but ask me again on Tuesday night when I'm in more of an extension headspace, and I will have another crack at it. But regardless, tune in tomorrow, and we'll be starting probably like at 10 or 11, one of those two times, and we'll be going till about 4 or 5 o'clock. So it'll be a much longer session, where it'll be our little last stop. So with that being said, guys, thank you for tuning in. Thank you for the donations as well. It's really appreciated. And